Good morning, Vananda. Welcome back to video lecture series, Linear Integrated Circuits and Applications. This is Dr. P SREENIVASUlu. Today, we are going to discuss about DC characteristics of op-amp. Under this, about input bias current. Already we discussed in the previous video. Next one is input offset current. Again, what is this offset current? You see, we consider an op-amp, a practical op-amp. Whenever if we connect the two input terminals, inverting and non-inverting terminals, to grounded, the output we are expecting 0. But in real op-amp or in practical op-amp, it is not going to be done like this. So previously we have seen, in the previous video we have seen input bias current. The input bias current is the average of two currents, that is at inverting terminal and non-inverting terminal. Now, today we see input offset current. Since the input transistors cannot be made identical, because if we take any two transistors, the two transistors doesn't have same beta value. The two transistors doesn't have same beta value. So there may be some slight variations between the beta value. So the characteristics, we draw the characteristics of any two transistors, definitely there may be slight changes. So that is the two input transistors cannot be made identical. There will be always some small difference between IB plus and IB minus. So what is IB plus? The non-inverting input terminal base. The current drawn by non-inverting input terminal base. What is the IB minus? The current drawn by inverting terminal base. So because of these two are not identical, so there may be some slight difference. So this difference is called offset current, IOS. Our aim is these two currents also need to be draw same current. These two currents means whatever the IB, whatever the current drawn by the transistor at non-inverting terminal, whatever the current drawn by the transistor at the inverting terminal, also we are going to be assumed are same. Then only the difference is 0, but it is not going to be exist in practice. So the input offset current is going to be right. The absolute value sign indicates that there is no way to predict which of the input bias bias currents will be larger. So that's why we are going to be take the magnitude of average. The difference between non-inverting current and inverting current is nothing but non-inverting current, inverting current is nothing but input offset current. Now in the suppose we see the offset current IOS, you see the offset IOS for a general op-amp using BJT. You see the offset current of the BJT version op-amp, 200 nanoamperes, 200 nanoamperes. And you see the FET version of op-amp. You see the FET version of op-amp, it is around 10 picoamperes. So from this, we see the BJT has more leakage current compared with the FET. See, FET is in the order of pico, BJT is in the order of nano. Even with the bias current compensation, offset current will produce an output voltage with input voltage VA is 0. So that is our problem. Now, the circuit diagram, what are the circuit diagram previously we have seen the circuit diagram. From the circuit diagram, again I will show that circuit diagram. In the same circuit diagram, we are going to be apply here for input bias current compensation and input offset current compensation. The circuit diagram is this one. You see at a glance again here, we are connecting two input terminals are 0 and we are expecting the output is 0. But here input offset current, whatever the offset current is generated here, the difference between non-inverting current minus non-inverting current and inverting current, nothing but IB plus minus IB minus. So it is the general circuit diagram we are going to discuss here. Now, you see here, V1 is equal to IB plus into R compensation. V1 is equal to IB plus into R compensation. So I1 is equal to V1 by R1. Already we have discussed about R compensation is the parallel combination of R1 and RF. Now I1 is equal to V1 by R1. Now at node A, I2 is equal to IB minus minus I1. So what is IB minus? Current drawn by inverted terminal. So what is the I1 here? I1 is IB plus R compensation by R1. So if we do this substitution here, V0 is equal to I2 into RF minus V1. I2 RF minus V1 is IB plus into R compensation. Now if you substitute this I2 value, previously we have seen I2 value is IB minus IB plus into R compensation by R1 into RF minus IB plus into R compensation. We substitute all these things. Finally, if you see output voltage, RF output voltage, RF output voltage is equal to RF into magnitude of IB plus minus IB minus. So this IB plus minus IB minus is nothing but offset current. Now, in a 741 IC with a BJT version, you see the output voltage because of this offset current. RF is a 1 mega ohm. We take RF is a 1 mega ohm, and offset current is a 200 nanoamperes. It is equal to around 200 millivolts. And because of this offset current, the offset voltage is generated at the output is 200 millivolts. So it is very high value. Whenever we want to use this op amp in millivolt applications, so it is going to be dominated in nothing but a noise. So noise is going to be dominated. So the purpose of using the op amp is going to be waste here. So you need to minimize this effect. So that's why in order to minimize this effect, the only thing is we need to reduce the RF value or you need to reduce the R1 value. It is the alternate way. So if you reduce the RF value, the gain is going to be affected. If you reduce the R1 value, it is going to be take more loading effect on the signal source. So that's why there is an alternate way to compensate this problem. We are going to be connect a simple T network. A simple T network at the feedback. So by using this T network, and if we convert this star delta form, we convert this one into star delta conversion. From star to delta conversion, you will get this values, and the values if we calculate from the star to delta conversion, RF is equal to RT square plus 2 RT R2 by RS. So finally the value is RT is less than RF by 2. So somewhat it is going to be a compensated compared with the original circuit diagram. It is about input offset current. And next one is, it is a if you see this total offset voltage, the total offset voltage is nothing but like a superposition concept. We can calculate bias current, and if we calculate offset current, and then we can add these total VOT, total offset voltage is equal to 1 plus RF by R1 into UOS means offset voltage because of input bias currents generated plus RF into IOS, input offset. Now one more parameter we need to discuss, thermal drift. You see this thermal drift. Now the bias current, offset current and offset voltage change with respect to temperature because the internal circuit setup of op amp is a transistor or FET. The transistor and FET parameters are affected by the temperature. So it is very important point we need to remember. The circuit carefully nulled at 25 degrees centigrade may not remain so when the temperature rises to 35 degrees centigrade. Suppose we are designing a circuit at 25 degrees centigrade and we have taken all these considerations. What is the input current, bias current, offset voltage, and we have nullified that voltages to whatever the offset voltage is. Whenever if you connect V1 and V2 are going to ground, so the output voltage are going to be get 0 for a practical op amp at 25 degrees centigrade. If you see the same characteristics, it is not going to be maintained at 35 degrees centigrade because the whatever the parameters input by transistor parameters, these are all are affected by the temperature. So this is called thermal drift. Often offset current drift is expressed in nanoampere per degree centigrade. Nanoampere per degree centigrade. Offset current is going to be expressed like this. For degree centigrade, how much current is going to be changed? Offset voltage due to drift is going to be expressed in millivolt per degree centigrade. This indicates the change in offset for each degree Celsius change in temperature. So it is also we need to consider in the DC characteristics. Okay, there are very few circuit techniques that can be used to minimum offset, minimum thermal effect drift, carefully printed out circuit boards. So it is not required here. You simply remember because of this temperature dependent parameters internally whatever you have generated, these are temperature dependent parameters. So even though if you design a circuit diagram at one temperature, this is not going to be maintain the same value at another temperature. It is the concept of a thermal drift. Okay, we will see in the next one.